where we started to talk about capacitors. Right now we're going to talk about capacitors in equilibrium. So we're not going to worry about the amount of time it takes to accumulate the charge. We're going to look at the point in time when it has been charged. So when a capacitor is connected to a battery, charges move until the electric potential is the same everywhere connected to the positive end of the battery. So the electric potential is the same everywhere here. And the electric potential is the same everywhere over here. And that's because electric potential for any conductor in equilibrium has to be the same. Now, the left-hand side is a higher potential than the right-hand side. The battery has a potential difference across it, some delta V. I'm going to call this delta V total. So sub T. Just, you can't get more voltage in the elements of your circuit than what the battery is supplying. Okay, the battery is the final say. So the battery supplies some delta V. In this case, since equilibrium has been reached, the left-hand side all reaches one potential, the right-hand side all reaches one potential. So the capacitor ends up with the delta V as well, a potential difference. And in this case, the potential difference across the capacitor is the same thing as the potential difference total for the battery. Now, charges had to move in order for this to happen. So this plate became positively charged. The other plate became negatively charged. So what we want to do is to look at a relationship between delta V, the potential difference the capacitor has, and Q, the amount of charge that accumulates on either plate. One plate ends up with a positive Q, the other plate ends up with the negative Q. They have the same magnitude, just opposite in sign. Now, taking this a step back, we know there's an electric field now between the plates. And we know potential difference, magnitude-wise, is simply the electric field times the distance between the plates. I'm leaving the negative sign off. There was a negative sign in the equation. I'm leaving the negative sign off just because it doesn't really matter. One plate's higher than the other. The electric field is constant between the plates of the capacitor. That's why we did not have to integrate.
This would have been nice to know during the homework over the weekend.
Well, we covered this.
I know, but still, I couldn't remember it.
So electric field. Electric field between the plates of a capacitor we know is eta over epsilon naught. Eta being the surface charge density of the charge. So delta V, we know eta is charge per area. So we get a relationship here between delta V and the charge itself. This is the delta V for the capacitor, so I'll put a subscript C on it. If we solve for the ratio of charge over potential difference, the ratio of how much charge accumulates on the plates of the capacitor versus the potential difference across the plates of the capacitor, we get a quantity here of epsilon naught times A over D. Epsilon naught is our constant. A is the cross-sectional area of the plates, the part of the plates that overlap. And D is the distance between the two plates. The ratio of charge per potential difference is completely and totally dependent on the physical makeup of the plates, how they're physically made. This quantity is called the capacitance. We use a capital C to represent it. You can think of capacitance kind of as the capacity. Capacitance is the amount of charge your capacitor can store compared to the potential difference supplied across it. So we can say C, the capacitance, is Q over delta V, which is a nice simple relationship that works for any capacitor. If you know the capacitance of your capacitor, you can figure out how much charge your capacitor can hold at any given voltage. This equation up here, the epsilon naught A over D, allows us to find the capacitance for a parallel plate capacitor. That's assuming there's air between the plates. Now, when a capacitor is constructed, it's very common to put something else between the plates. For example, you can make your own capacitor with 2 pieces of aluminum foil, but they can't physically touch. If they physically touch, that'll allow charges to transfer between the two, which would defeat the purpose. The purpose of a capacitor is to be able to maintain that charge separation so that it can store energy, which can be used later for other purposes. It's common to put something in between the plates, and we call that a dielectric. Kappa is called the dielectric constant. If you put a material in the plates that can easily create electric dipoles, remember an electric dipole is just a little separation of charge between a positive and negative charge. If you put a dielectric in between the plates, you actually increase the capacitance. You increase the amount of charge that capacitor can hold for any given potential difference. Okay? Kappa is just 1 for air. So if there's just air between your plates, that's why the equation is simple to just be epsilon naught A over D. So having something between the plates, having a dielectric between the plates increases the capacitance, which, looking at this equation, if you increase the capacitance, that can increase the charge for any given delta V.
What's a really, really good dielectric?
Wax paper works pretty well. Paper works pretty well. There's a small chart in your book that has a few sample dielectrics. I don't remember them all off the top of my head. Pure water without any impurities in it would be a good dielectric as well. But it's hard to get nice pure water. Okay, this equation, fabulous relationship. Q is the amount of charge on either plate. Delta V is the potential difference across the capacitor. C is the capacitance of the capacitor. I'm going to use that equation quite often, actually. It's a simple equation, so it's nice. Another equation we're going to use is the energy stored in the capacitor. When there is charge that has accumulated on the plates of the capacitor, then the capacitor will be storing energy. For example,
U is the potential energy, and V is the potential electric.
V is the electric potential, so voltage, and U is potential energy, so joules. So I have here a capacitor. This is a 1 farad capacitor. By the way, I didn't mention that to you. The units of all this get messy. We call the units a farad. So capital F.
Just charge per volt.
Charge per volt is also something else that we'll work out too. So coulombs per volt is also appropriate. All capacitors, have what's called a breakdown voltage. So this capacitor is 1 farad. Whatever it's made of, its cross-sectional area, the dielectric between the plates, the distance between the plates, makes it 1 farad. But this capacitor has a breakdown voltage of 5.5 volts. That means if I try to apply anything greater than 5.5 volts to this, I basically blow it up. I ruin it. It's no longer useful, can't be used again. But that's not a concern with this little hand crank generator. So, hand crank generator makes charges move, so I'm charging that capacitor. But if I let go, it's going to discharge. If I disconnect the hand crank generator from the capacitor, it's not doing anything. If I hook it back up to the capacitor, it discharges. So the energy is flowing back out from the capacitor in through the hand crank. You have to have a complete circuit for that to happen. It can't discharge without having a path to follow through. But that energy can be used for other means. Now, this isn't necessarily a real practical example. Mentioned last time the flashing your camera, for example. Flashing your camera needs a whole bunch of charges to move through it. It needs a decent amount of current in a short amount of time. And the battery of your camera is not capable of doing that. So the battery by itself can't get the flash to happen. So what happens is it charges a capacitor in there, and whenever you click the button to take a picture, it flips the switch and connects the capacitor to your light bulb. And the capacitor discharges and you get a nice flash of light.
So is there certain capacitors that discharge quicker than others?
The rate at which capacitor discharges depends upon the capacitor itself as well as the resistance in the circuit. We're going to talk about resistance next. So it depends upon how much the circuit resists the flow of current.
But in your camera, you want really low resistance, so you
Correct.
can do it quick.
Yeah. You guys want to play with it?
Yeah. How can you not want to play with it?
Toys. Toys are always good. So the capacitor.
So it doesn't matter which way you turn it?
No. The capacitor stores energy as long as it has charge on the plates. As long as there's an electric field between the plates of the capacitor, which happens as long as there's charge, then there's energy. There's a few ways we can write energy. We can write it in terms of a potential difference. So the energy depends upon the capacitance itself, and it depends upon the potential difference. But we can use this equation, and in place of C, we can put Q over delta V. So we could write this in terms of Q and delta V. In place of delta V, if we solve this for delta V would be Q over C. If we put Q over C in here, we get Q squared over C. So basically, if you know any of the 2 out of the 3 terms, you can find the energy. It doesn't matter which 2 terms you have. So there's energy stored, potential energy stored in that capacitor as long as there is charge on the plates. If there's charge on the plates, that means there's a potential difference. Okay. So these 2 equations are going to be very handy as we look at capacitors. Questions so far?